All right. So we're going to talk a little bit more about reflection and refraction, and then we'll get into images and lenses and images. We're basically following the class schedule exactly. If you are following along the class schedule and doing the reading, we are right on schedule. Except I think we're supposed to do this internal reflection part Friday, but other than this 5 minutes here, we're right on schedule. Let's see. So what I want to remind you about to get started is that light does both. Light both reflects and refracts at a dielectric interface. Remember, that just means a plane where you go from n equals 1 to n equals 3, 1.5 or whatever. Right, here we go. All right. Light does that. Here we go. Turn off Bluetooth, hide the watch, etc., etc. Maybe I'll actually get messages. We'll see. So what is it? Let's draw it. Let's remember, first of all, dielectric interface. That sounds complicated. No, this is just air here and glass there. There's a dielectric interface, the surface of glass. So, this is glass down here. I don't want to draw lines on it because I got to draw other lines on it. So if light comes in like this, right, I'm going to put an arrow to indicate which way we're thinking of the light going. You know that everything important is described with respect to the normal. So then we draw our dotted normal. Normal means perpendicular to the surface. All right, it's not a judgment. Okay, and we define an angle with respect to the normal. We're going to call it theta 1. 1 because it's in index 1, I guess you could say. And we'll call this index 2. Okay, so the point is two things. All light will always do both. It'll reflect and refract. Okay, so reflect is the part that does this. It reflects. We'll put an arrow on it, and we'll say, let's go ahead and give it a different name, theta 3. So the law of reflection tells us that theta 1 equals theta 3. Right? Law of reflection. There's a little bit of review of what we talked about before, but we'll get to the interesting case in a minute. Right? So those are going to be equal. But then we know the light also goes into the material, or into the dielectric, and we know that the angle actually changes. It's not theta 1 equals theta 3. In terms of, words, it falls towards the normal if it's going into a higher index, because it's tiring to go into a higher index. And we'll call this theta 2, and I picked those numbers so that 1 equals 1 and 2 equals 2. So theta 1 is the incident angle in material 1, theta 2 is the transmitted angle in there, and of course this is Snell's law. Right, so N1 sine theta 1 equals N2 sine theta 2. And that is all of that is all of geometrical optics. It can all be described with those simple equations, okay? But, so the question is there any way for this to get interesting? Yes, believe it or not. So this, what we have talked about, is called an external reflection. This whole thing has been external because we went from low N to high N. Okay. So you've thought a little bit about external and internal when you're thinking about phase shifts. What are phase shifts? We're doing geometrical optics. There are no phase shifts here. There's no amplitudes or phase shifts. There's just lines. But external and internal does have one effect, even in geometrical optics. So let's now do an internal reflection. Okay, and say, well, it's probably the same thing. We'll draw it like this. And I think I wanted to go ahead and, put N1 on the top and N2, 1.5 on the bottom. Right, so that's all the same. And all we're going to say is that for internal, we're going to go from the high to the low. Okay, so our incident ray is just going to be down here. That's the only difference. And you might think, oh, physics loves symmetry. It's all symmetric. Everything will be the same. No. Something will be different. Okay? Even though this is the initial ray, I'm going to call it theta 2 because it's in medium 2. All right, so theta 2. And we can say, well, what's going to happen? Well, you're still going to get reflection, right? Reflection is the same. You will get an internal reflection. Theta 2 equals, and we'll call this one theta 3, just to match. Right, you'll definitely get a reflection. Theta 2 will still equal theta 3. Before we said 1 equals 3 because we started in medium 1. Now we started in 2, so theta 2 equals theta 3. Well, how is Snell's law different? Snell's. Or let's see, how is it physically different? It's physically different because now the light is breaking free of the high index. Okay? So instead of going straight, it's going to flee the high index like that. Or it's going to flee the normal like that because it just broke free. Shawshank Redemption. So theta 2 is right there. Okay? So Snell's law now, theta 1 is right there. So we went from 2 to 1. So Snell's law is now N1 sine theta 1 equals N2 sine theta 2. It's the same, right? It's not different. It's just, you can't change Snell's law. Okay, so this has been an internal reflection. Ah, yes. All right, and that's from high N to low N. So you've already had to think about these. One of these makes a pi phase shift and one doesn't in your current homework you're obsessing with, or last week. Let's see, which one makes pi phase shift? This one. Pi phase shift here, no pi phase shift here. But now we're doing geometrical optics, so we don't care. It's just a line. Okay? So let's see if anything interesting is going to happen. I need a piece of glass. No. Yes, I do have to get a piece of glass. Let me get a piece of glass real quick. Oh, it doesn't have to be glass. Oh, dear. Whoops. Let me get a piece of glass. I forgot. Yes. Okay. Because we actually want to think a little bit now about how much light reflects. Okay? So back when we were talking about interference and everything, we said, well, it's about 4%. Okay? Because that's why we said when the light reflects off, 4% reflects off the front, 4% reflects off the back. Let's interfere these two rays. And I told you it's 4%. And we also said if you look at yourself in kind of a piece of glass, you know that you see like a ghostly image of yourself, you know, that you can see through. That's because you're getting 4% of the reflection here, but you get a lot of the light coming through here showing you the background. So if you see yourself all ghostly, it's because it's only 4%. But that's at vertical, that's at normal angle. If you change the angle, it gets different, okay? So I'm not going to do the math because we don't have time. But if we change the angle, it gets bigger for external reflection. Like when I look at you at an angle like this, see how it's like not ghostly anymore? See, you can't see because it's far away. What's up? Right? It's all not ghostly. Now it's like 100%. Here you go. Now you look at somebody else that you want to look at. At a steep angle, you'll see it goes from like 4% to like something much higher. You can also do it in a table. If you look at the glass in a table, suddenly it looks much brighter. Any dielectric surface, okay? So we're not calculating these reflection coefficients and the intensity of the reflection. I just want you to know that it does vary for an external reflection, okay? But where it gets interesting is if we think about an internal reflection. So let's think about internal real quick. Let's see. So the external reflection actually goes to 100% at a complete 90-degree angle. But then you can't really use it as a mirror anymore, you know. So let's see. Let's let internal get interesting here. Okay. So internal reflections get interesting at large theta. I'm going to write incident here, and you're just going to have to understand that that means theta 2. Okay? I don't want to write theta 2 because it won't always be theta 2. You might call it a different number. But you know what INC means. It means incident. Okay? So let's draw a bunch of cases of different angles of incidence on an internal reflection. That will be exciting. N1 equals 1, N2 equals 1.5 with glass here. So a thicker piece of glass. Somehow we're inside the glass, right? And we're like sending light out and seeing what happens. Right, so if we bring it in at a small angle of incidence, what's going to happen? Well, this is going to reflect at a small, it's going to reflect at a small angle of incidence like that. I'll draw the reflected ray dashed. And how is it going to refract? It's going to run away from the normal. I won't draw it dashed because the normal is dashed. I'll just draw it daintily. There we go. And then this ray is going to flee the normal a little bit like that, right? So it bent away. And if we had one come in like this, it would reflect like that, right? And then it's going to flee the normal more. Oh, okay. What if one came in? These are out, right? These are reflected. What if one came in maybe this steep, right? What's going to happen? You notice this angle is getting bigger, isn't it? Right? But then the reflection is just following the law of reflection like that. Right? So if we go up here, higher theta incident, we go down here, which really is higher theta refracted. Okay? So both of those are higher. This is farther from the normal, farther from the normal. But the problem is we have this factor of n difference here. Like 1 is 1 and 1 is 1.5. So that is making this angle bigger. Right? So bigger angles. Okay, I'm totally off the rails here. So the question is, what happens if we go further than this? Look, this can't go any further. What do? I've done it before. You pull the laser beam here, and you can't push it any further. It's like, I can't. No, not really. I'm going to show you what happens. We're going to watch it through the magic of videotape here. Well, not really videotape anymore, but that's something people used to say. So it'll be easier to see if I just play the video of it doing the same thing. La la la, it's your generation, here we go. And shit, it's on the wrong side. I'll switch the projector sides, I think. Screen controls. Oh, shit, I can do that. Okay, hold on, do that. Let's just bring this one down. Okay, so what we're going to watch is what happens when you take that angle past this critical, if I may use that word, value here. Okay. And, oh, Jesus. I love the lights. Let's see what happens. I think you'll be able to see the ray. So here, this person is like holding the laser pointer, running it around. And here you can see the angle of incidence is big, but it's small here. And as we drag it this way, it's going to get bigger and bigger. Right, I always got to talk. La la la. Oh my God. And like see here, you see it is refracting out. So it's like going up and over. What happens when we go too far over? We're about to get where the refracted one. Well, look at that. The whole thing suddenly reflects right at this critical point. Look at that. Let's do it again. Do it again. Wow, look at that. Right there. Oh, we can't get enough. And then there's one little special effect you might have missed here. If you look really close, watch. Oh, God, no, this is a long video. Let's see. Watch what happens the first time we start to hit it. Watch over here. And you can see what the refracted ray does. You'll see that this thing shows up right when the refracted ray gets all the way to 90 degrees. You know, I thought, was there a Wi-Fi study on campus, right? I got to download these myself. If you guys would pay more tuition, we could make these work. Okay, here. Oh, okay. So there it is. You see the refracted ray is going to go down. And if you watch right when it happens, watch right here. You'll see it's right when it comes down to 90 that it really, there it goes. Did you see it fly by? And when he pulls back, you might, there it goes. Right. So this really is happening right when we run out of room for the transmitted refracted ray. Is really when this is going on. Okay. So now that you've seen that's real, now let's do the math. Now that we've had to watch it, let's do the fun part. Let's do the math. It's going to go away, and this is all going to come up. Oh, my God. Wow, this is like... All right. The milky fish tank. So then the answer to what happens is, let's go a little bit higher angle. And it's clear. If we go even higher, don't do it. I'm going to do it. We're going to go even higher. Nothing refracts, and instead of these dainty lines, it all goes down into the thing like that. all 100%. It doesn't amplify. Okay, I just got a little excited. Okay, so the angle that this happens at is called the critical angle. Okay, so if, here we go. When is it going to happen? If the internal theta incident is greater than the inverse sine of what? Of n low over n high. Right? That's basically the angle where this happens. Okay? And you can figure that out. I meant to write it here. You can figure it out by saying, when does this happen? When this angle equals 90. Right? As soon as this angle equals 90, you go any bigger, and then you get it. So you just have to do the refraction case for theta 1 equals 90. Theta 1 equals 90 degrees, right? Because that's this angle. So you'd say 1.5 times the sine of theta 2, that's what we're looking for, the angle where it happens, equals 1 times the sine of 90. Okay? What's the sine of 90? You got to be good at that stuff. That's 1. And that's really n1, and that's n2. So you can see, if you want to solve for this angle where this happens, it's n1 over n2, and then you take the inverse sine. n1 was the low index, n2 is the high index. Okay? If you're always in error, you can say, well, that's always 1. So you might say it written as 1 over n for the material, because that n low is usually where the other side might be error. Or the other side might be something else. Okay? So when this happens, it is the famous thing called total internal. It was named by a Valley girl. Internal reflection. And it is 0% transmission and 100% reflection. So what you need to know about that is how to calculate the critical angle. And we'll somehow find a way to turn it into a homework problem. Right? I mean, we'll probably combine it with a little bit of geometry. How do you know it is 90 degrees? Because that's the case where it can't have any further to go. Right? 90 degrees. It can't go to 91 degrees because then it's inside the material. So the beam literally jumps from here to here instantaneously. Okay, as you change the angle here. That's why you were suddenly seeing this beam light up, is this beam was hitting 90 degrees, and it can't go further than 90 degrees. We could show it with math more detailed and show you things go imaginary, but we aren't going to do that. What does it say in the thing for the inverse sine? That's n low over n high. N low over n high. Right? And so does internal reflection happen at angles less than 90? Does internal reflection? Yes. There was reflection here. You just couldn't see it in the demo. If you got all the lights out and there is some reflection, but it goes from, well, at normal angles, it's 4%. Okay? As you go bigger, it gets a little bigger, kind of like the piece of glass you looked at, but then it just suddenly goes to 100%. Okay? But there is some reflection here. That's like all of homework 3. There has to be reflection there. Right? The back reflection on the interference films was an internal reflection. Okay. So we could think, how are we going to make that into that brilliant concept into a homework problem? And I haven't done it yet. We'll have the homework up on time this week, which means Wednesday at 11:59. But you could imagine you could have a case where you have like a glass wedge, and you have rays coming in like this, and you'd have to say, okay, which one is going to be totally internally reflected? So you have to think, okay, well then they go this way, and they go this way. And the way I drew it, clearly neither one of them is going to be, right? Because they're both way too close to normal. But if this thing were like that, right, then this might come in, and this one might come in at a different angle, right, like that. And you can say, which of these two is more likely to be totally internally reflected? Or if you were doing numbers, you could calculate it, and it would be this one. Because this one's coming at a steeper angle than this one. See, if we draw it to the normal, so you can see, since this one is bent down, this angle is bigger than that angle. So maybe this one would be totally internally reflected, whereas this one could still transmit. Okay? So, there's not that much to it. It's just one simple formula. But you got to understand the idea is that things at steep angles go through total internal reflection. All the films and interference we did were not at nearly steep enough an angle. Those were all vertical. Those were all incident angle of 0. So this is a different case. And this is how fiber optics work. This is why a fiber optic cable can transmit light for kilometers, is because you send the light in at a really steep angle and it just bounces off the walls and goes all the way down. All right? So that's the last little thing about reflection and refraction and transmission that we need to talk about. All right? Now, we're going to talk about lenses and imaging, how to make those things happen. Let's see. This is the one that doesn't like me. Okay, lenses and imaging. But it looks like there's one last question about total internal reflection. What could it be? Does total internal reflection happen when it is exactly 90? Which angle is 90? Okay, yeah, so we calculated it for the case of, okay, I guess it's if the internal reflection is greater than this value, right? This is the case when the refracted angle is 90 into the air. You'll get this value, so it's greater. That's why there's a greater sign there. Total internal reflection happens when your incident angle is greater than that. And the transmitted angle, you would actually say, doesn't exist anymore. Okay, it's because it's just no light is transmitted, so the transmission doesn't happen anymore. Okay, I'm through with that side. I don't deal with that side anymore. Okay, so now let's think about how to make an image and lenses and that kind of geometrical optics. Who here likes to draw? Imagining 200 hands shooting in the air, doughy-eyed. Yes, we love to draw. Well, if you don't like math and you like to draw, have I got a lecture for you, okay? This is the next subject. Everybody loves this part of the class because it's not quite as hard as other parts of the class. Although if you find it hard, that's okay. You're just, you are a few sigmas out and whatever, okay? So a lens, you're good. I mean, there's nothing wrong with hating this and loving interference. That's me, okay? What is a lens? Let's go motivational speaker again. What is a lens? All right? Look at this lens. There's some serious, like, Hogwarts shit back there if you get into the big optics. Let me look at this thing. Okay, it's a glass surface. Oh, it's so heavy. It's a glass surface curved. I have a brilliant definition here. So that parallel rays are going to do what? Focus to a point. Focus to a point. That's really all it is. All right? Now, they got to make it pretty special about the exact geometry of how that happens. But I can't even lift this thing. Okay? So if we're going to draw it, then we're going to draw it like this. So usually the shape that does that is like this, right? It's like curvy on the out. It's outside curvy. So it's convex. All right? So a convex or converging lens is what we're going to look at first. So convex means something that sticks out. Okay, so as the light approaches it, it sees the glass sticking out. And it causes light to converge. So you draw it like this. Okay? Draw it like that. Convex lens. It can actually be convex on one side and flat on the other side. It can be a Fresnel lens, whatever. This is the symbol for a convex lens. All right? So you got to draw the lens. You got to draw the optical axis. Like that. Optical axis like that. I'm not going to label the lens. It's right there. And what happens is we have parallel rays coming in, hitting the lens like this. And they focus to a point. We call that the focal point. Right? So if we have a point here, then all the rays that came in parallel will switch, will get refracted and hit that point. Ta-da. Okay? Why does that happen? I mean, let's think about why is it, what's going on here? First of all, we draw it very approximate. We draw this wide curved lens, but we don't actually draw the detailed refraction at each surface. Okay, I'm really thinking of it just as a line where things bend just the right way. But let's think about it. This one didn't have to bend at all, did it? It just had to go straight. The one on the optical axis is going to go through the focus anyway. You could drill a hole in the lens. Don't do that. Okay? But does it need to bend, and will it bend? No, because it's hitting the glass normal to the surface. Angle of incidence is 0. Snell's law says the angle of refraction is 0. It continues along the normal. If we go up here, it does need to bend a little bit. But it's hitting the curved glass, right, at a different angle. And this one needs to bend more, but it's hitting the curved glass at a steeper angle. Right? That's why the curved glass focuses the light. It's because as you go farther and farther from the optical axis, the curvature makes the normal farther and farther angled away from the parallel rays. So it's designed just right that the change in the angle due to the curvature makes all the parallel rays go right there. Right? That's how a lens is designed. You know, we could go through the geometry. It's kind of painful, but we could. Okay, so I can show you that it really works. So if we have parallel rays, I learned this year you can use a projector for parallel rays. Let me write an AJP article about that. Okay, so here we have a white beam, and here I have my lens. God, it's heavy. Let me get this lighter lens, all right? I'm old. Okay, here we go. And I'm going to put it here, and whoa, it's going to catch the thing on. Ooh, I wonder if we could catch it on fire. Can you see that? You can't see it because the lens is in the way. This is a horrible demo. Here, maybe this bigger one will let you see it. Oh, does anybody have an ant? I want to burn some ants. Back in my youth here. Wow, look at all these images of the thing. Okay. But it's making this parallel ray become a point. What are you seeing? Oh, yeah. Oh, no, you can't see it. Okay. Okay, so it does that. All right? That's what it does. It can also do this. So go to the point the other way. It can also make a point source at the focus becomes parallel. Basically, anything that goes one way in a lens can go the other way in a lens. All right? So if you have an optical axis and you have a point source of light, right at this special place we're going to label F. That is the focal point. All right? If you put a source of light right at the focal point, it'll do just the same thing in reverse, like this. All right. Like that. Some of you are going to do this in lab. Some of you have already done this in lab. I meant to say at the beginning, we always have the labs trail the lectures by a week. So there's a chance that you have some idea what's going on. This is the 1 week we couldn't do that. So how many did this yesterday? Oh, good. Okay. See, so hopefully the lab manual explained it really well. Okay. Let's see. So let's see. We need the focal point, and then we need this other thing called F, which is really the focal distance. So that's the distance between the center of the lens and the focal point. F. Right? Focal. Let's see. I'm writing too big. I'm going to put it right here, and you can put it in your notes. The focal length F is the distance between the lens, and we mean the center of the lens because the lenses we assume are just thin. The lens and the focal point. So you might see people sometimes will kind of mix them up or be a little bit sloppy about it and just label it F. When you label that point F, you mean that's a focal point, and you also mean the distance from here to here is a number that goes with F. Like if F equals 10 centimeters, then this is 10 centimeters. And that F label there means that's the focal point. And it's 10 centimeters away. Okay? Let's see. Okay. So now let's think for a second about how does an image actually form. Let's see. So I've got that. There's a lot of math, but I've got it described as a sentence. I think makes sense. All right. I think I can use the back. I need trouble. Oh, that thing isn't clicking. There we go. There we go. Okay. All right. So let's think about image formation. Okay. Oh, fuck it. Image formation. Here we go. We have this thing called a lens. You put it on an optical axis. It's got a focal length and a focal point. What is that doing for us? Okay, so remember my objects when we talk about how light sources, there's two kinds of light sources, right? There's actual lights, and there's just objects that light bounces off of. And every point on the object is like a little source of rays going in every direction. So what object are we going to do? I have a tree here, but I'll draw anything appropriate that someone yells out. Excellent yelling. What? A hat. Cool. A Hat, yes. So my generation would be like a fedora, but you'd be like that stupid guy with the tall hat, right? What's that about? Right, so if we have, what's this guy? Who's that? Okay, if we have an object like that, it's like the Mountie hat, you know that guy? An object like that, and we have a lens like this. We got to think about why is it going to form an image. So each point on the object, this is what's really happening, emits rays. This is like we talked about when we started geometrical optics. Emits rays, which are focused by a lens to a corresponding point in space. So what it really means, so this is the non-mathematical, this is just the touchy-feely description of it, is let's take a point on this ferrule hat. Is that right? Thank you. Here, and it's going to emit light in all directions. Okay? That's probably 10 years old. And some of them are going to go, and they're going to be focused by the lens. Now, they're not parallel. Right? Parallel rays will go right to F, but, non-parallel rays will focus somewhere else. Well, they'll focus somewhere like, if that's F, then it'll be like all these rays that were the top front corner of the hat are all going to come here, say. Like that. Okay. And then what about, like, that's like the top corner. What about the brim here? Right, the front of the brim. All those rays will all enter the lens. I mean, they'll also go everywhere. Here I am looking at the hat, right? But then they will focus a little bit in front because that's like the corresponding position in space. So every point on the object will focus over there in a place that corresponds, and you'll get an image. Okay? So like the hat image would be like this. There's the brim, and there's the top of the thing, and there's the back. It'd be like that. Right? So everything here focused here. Everything here focused there. Right? Now, is there a hat there? Philosophically, I could argue that there is a hat there, but there isn't a hat there. Right? It's just an image. But if you put like a screen, if you put like your paper here, you would see an image of the hat. Okay? It's actually a 3D structure. It's not really just 2D. The imaging, the focus usually works best in a specific plane. So it really just makes a nice image in one place. But really, light from the back of the hat goes back here. Light in front of the hat goes here. It's sort of the full 3D thing is there. It just works best in one plane, which is why we think of the imaging as a planar thing. Okay? If I had my can of smoke, there'd be like something that wouldn't look like a hat at all. You'd just see some light there. Okay? So what we'll do next then after the break is we'll talk about how do we describe these rays mathematically and geometrically. We can't really just do this and say, oh, there's a hat. Right? We have to do a little bit more than that. I know you're dying to know how to get the precise location of the hat, so I don't want to make you wait any longer. I got one question about the hat, which was, is the hat actually emitting light or just reflecting it off the sun? That depends on what kind of a hat it is. If you've ever been to a New Year's celebration, sometimes the hats actually emit light. But remember, when we first started geometrical optics, I told you there's two kinds of sources of light. There's actual sources that have light coming off, and then any object is a source of light because light can bounce off of it. So you said, yes, it didn't have to be the sun. It could be the room lights, but some sort of light is bouncing off the hat. Okay? So now that was just a cartoon of what happens when you make an image. We want to get the precise. Yes, we have to do it precisely. Location and size of the image. We got to use something called 3 easy rays. At least that's what we used to call it. All right? To get it, all you got to do is draw 3 rays. You actually only have to draw 2 rays. So if you can only remember 2 of the 3 easy rays, you're still going to be okay. Okay? But see if you can remember all 3, because they're all exciting. So to do it, you draw an optical axis. Okay? Thanks. I know. Yes. And you draw like a lens on it like that. And you got to specify where the focal point of that lens is. So that's why we put like a point here with an F and a point here with an F. And they should be the same, it's the same distance from each side. See, now somebody made me nervous. Okay, all right. Damn it, that's not the same. Hold on. There, that's what I'm trying to do here. Oh, okay. Okay, there we go. Okay. And now we need an object. And I'm not going to draw a hat because I've got to draw like 50 of these. So here we go. The standard object to draw is an arrow. Okay? It could be a hat. It could be anything. It's just an object, spatially object. And just like anything else, it has rays coming off here. It has rays coming off here. It has rays coming off everywhere. But we're only going to draw a certain 3 easy rays. Okay? So the first ray, 1, straight. That's easy. And then, what do you do when you hit the lens? Oh. And then what do you do? If this one, where is this one going to go? Through the focus, yes. Because we said that's what a lens does, is it focuses parallel light to a point called the focus. Okay, so that ray is going to go like that. Very nice. We'll get rid of this F here. We'll put it up here. Easy ray number 2. Straight through what? The middle. Let's think. Remember when we sent the light through the plane of glass and we showed that in the end it didn't really change its angle? It refracted in at an angle and then refracted out at an angle. Well, the ray that goes straight through will see the same angle of the glass on both sides. The ray that goes straight through the middle. So it's kind of the same thing. So that ray you can just approximate as going straight. Like that. Okay? That's easy ray number 2. Easy ray number 3 is through the front focus. Just to not get mixed up. And then straight. This one maybe is not as obvious, but let's draw it and realize, oh yeah, that is obvious. Okay? So another ray coming from here would go through there. And if we imagine it was parallel light coming this way, it must be straight. Dude, without even cheating, those 3 rays cross. Look at that. Wow. So what that means is the image is here. This is the real image. And apparently it's inverted because the top is on the other side. Okay, I wanted to label that as real rays converge at the image. At the image. No, I'm sorry. Rays converge at the real image. That's what I meant to say. Real image. Okay? That's what's happening right here. And my image, my little arrow is kind of running into these rays. It's a little hard to tell. But there's the image of the arrow. Okay? If I were to do the same thing from here, it would land here. If I were to do the same thing from here, it would land here. If I did the thing from this tip of the little arrow, it would land on that tip of the little arrow. We could sit there and do that for every point on the image. The reason we use an arrow is that instantly tells us everything about the image. It's kind of how tall it is and where it is. That's all we care about. We could do it just with a line, but that would be confusing. We don't want it to be confusing. Okay, so we draw an arrowhead on it. Right? That's it. If you can only remember 2 easy rays, it would still go to the right place, but it's always good to have that third ray, you know, just to see 3. It makes you feel better. All right. So now we're going to do like a bunch of different places. Oh, you're going to be so sick of the 3 easy rays by the time I'm done with you here. So the nature of the image depends on the position of the object relative to F. And remember, F is the focal point of the lens. So it matters where you draw the object. So let's do a case with the object really far away. All right, so here's the lens. Here's a focal point. And here's a focal point. I'm not even going to label them. I'm a wild man, okay? And I'm going to put this thing way out here. Don't do it. No, I'm going to do it right there. Look at that. Here we go. 3 easy rays. You want to do them backwards? No, we better not. Let's do them straight ray. Okay, number 1, straight. Okay, to the lens. Like that. Oh, this is the hard one. Most professors will get out at like a straight edge, but come on. Please. Oh, shit. Oh, there's that one. Okay. And then this one is going to go through the front. That was number 2, straight through. And now through the front focal point. Whoops, to the lens. Oh, dear. Boom. Okay, I suck at this. That's the hard. I shouldn't have done the hardest one first. I should not have done the hard one first. Which one? Oh, it's this one. What the hell's that? That's the problem. It's supposed to do that, and this one is supposed to do that. There it is. There it is. I don't know why I turned right through the middle of the lens. Okay, so really far away, put it kind of like that. Interesting. Let's put the object at 2f. Right, this was, I meant to label this. This is really far. Really far. Right, and then you have like an optical axis here, and you got a lens, and you say here is f, like that, but we're putting the object at 2f, like that. Object at 2f. Here we go. First ray. No. Second ray, the easy rays. Third ray. Boop, 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 boop. There we go. So you can see when this thing got closer, it looks like it kind of pushed it farther away a little bit, right? It got farther away. And it's also about the same size. So we're going to show that mathematically in a minute. This one looks like smaller. Interesting. Very interesting. So now we're going to do a couple more cases, and then we'll do the math. Let's see. So we had it far away. We had it at 2f. What about just outside f? Let's do that case. Let's see. Got to plan ahead here. Optical axis like that. Lens like that. F. Right. So there you go. Just outside f would put the object like here. Right? Okay. 3 easy rays. Number 1, straight. And through the focus. Number 2 is going to go through the center. Oh dear. Got a little curvy there. And number 3 is going to go through the focus. And if you didn't draw your lens big enough, you just pretend. Okay? You just pretend. And it goes like that. Okay, clearly this middle ray is the hardest ray to draw. There we go. Okay? So when you get it near the focus, look what happened. It got really big and magnified. All right, it's huge. Look at it. And you can imagine if you got closer. Well, that's what we're doing next. Let me not get ahead of myself. Okay? So let's write. I had some notes on what these are supposed to be writing here. So here, let's go back. Let's just think about it for a minute. When we had it far away, it was inverted. Right? It was shrunk. And what else was it? And it's a real image. Real image, an inverted shrunk real image, and it's just outside f. Just past f. Sorry. I got so excited to draw. Right? But you can see what that is, like a real inverted image just outside f. Here, when we were at 2f, what did we get? We got inverted. It's about the same size, I would say. Right? And it's at about 2f. So that's like a 1-to-1 imaging situation there. If you put something at 2f, you get an image at 2f. Interesting. And then here, what do we get here? Just outside of f, this looks inverted. Of course. It looks magnified. And where is it? It's far away, I believe is the one. Yeah, far behind the lens. Far past f. Right? Because here's f. It's way over there. So you can see as we bring this in, you can almost imagine what it's going to do. It's like this little image, and it's growing and getting farther away. And then we're going to go crazy. We're going to put the object at f. All right. Object at f. Lens. Focal point, optical axis, and we're going to put the thing right here. Oh my God. I can draw one ray. Easy ray number 1. Straight to the lens. and like that. Easy ray number 2 is going to go through the center like that. Right? And how do I draw easy ray number 3? I can't. Right? Well, it goes down. It's got to go through there, and it'll never hit the lens. Right? Since that line is coming straight down, it's parallel to the line that is the lens. It's never going to hit the lens. So easy ray number 3 died. There is no easy ray number 3. Oh dear. I'll get to that in a second. Okay, so what we have here is no image. Basically, we get nothing. The light just comes out parallel. Yeah. Or you could say it's infinite inverted at infinity. I mean, you could say eventually those rays will come together. If you go to infinity, they won't. Right? So the point is, this really doesn't do anything. There, you get nothing. Okay, there's one more case. Are you ready? We're going to keep marching in here. And we're going to put it inside the focus. Wow, like that. Focal point here and here, and put it there. Wow. What are we thinking? Well, 3 easy rays. Maybe we can still do it. Oh, give myself a little room. First easy ray, it's not different, right? Straight through the focus. I missed. Right? Second easy ray is through the center. So maybe you already see a problem here. Those two are diverging. They aren't going to converge to anything. And now we have a problem. We can't draw back here and hit the light, but what this one does is you can draw one as though it were coming from there and go straight and then come out like that. So this is our original 1, this is 2, and this is now 3. Right? And why is that 3? If you think it actually makes sense. Oh yeah, if parallel light comes here, it goes through the focus. So you draw the ray that also goes through the object point that you're talking about. Okay? So this is new. This is object inside F. And the result is diverging rays. Right? No real image. Right? But stay tuned. Or ask your friend who already did the lab, because we'll get an image out of that somehow. Okay? So all that was done with zero math. Right? That's just drawing. So we like drawing, protractors and stuff. Yeah, good. Now we're gonna. Wow, it's like I'm camping here. We're going to repeat this with one equation. We're going to solve all this with one equation. One equation basically makes this all work. It's a pretty simple equation. I wanted to keep all these. Oh well. You have them in your notes. Okay. So we're going to do all this with the thin lens equation. Okay, so now the math. Now instead of the 3 easy rays, let's do the math. So if we're going to do it with math, we have to label some of these distances appropriately here. So you got the lens on the optical axis, you've got an F here, and you got an F here. Right. So when you are talking about your object, then this distance is the object distance, S. Right? So S is the object distance, and it is what I labeled there. It's just from the object to the lens, right? Object distance. And you know this is going to make an image. Here I drew it at about 2F, so you know it's going to make an image like that. And that, from the center of the lens, is S prime. Right? S prime is the image distance. And you know F is the focal length. We label the point F, but we also mean that's the distance to the focus F. Right? So all we've done really is add S and S prime. How far away the object is, how far away the image is, and then we apply the thin lens equation. And here it is, 1 over the object distance plus 1 over the image distance equals 1 over the focus. That's it. Really, in optics, everything is about inverse quantities because those are really what matters. but we write them in terms of the physical quantities 1 over, just because it makes it easier. Okay. This will tell you where the real image is, because it's telling you that. It doesn't tell you how big it is. For that, you need magnification equation. All right, the magnification equals minus S prime over S. And you can imagine what that's defined as. It's the height of the image divided by the height of the object. Right? That's what magnification means. I don't want to write it that way because then you'll think that's a fundamental formula. Just think about what does magnification mean in regular English. Now, I missed some questions here, so you keep drawing. Let's see. Why are only some of them real images? Everything I've drawn is a real image. I just forgot to label it real image. So we haven't drawn anything that is not a real image yet. Why did ray 3 go up? I'm sorry, I didn't catch this in time, so I don't know. Ray 3 went up because the normal way to do the 3 easy rays is the third ray goes through the focus and then parallel. We can't really do that when it's over here. Okay, you could draw like that, and then right, it can't get to the lens. But what you do know is a ray that did this would end up going parallel. So the way you draw the third ray, if the object is inside the focus, is you imagine light coming from the focus that goes through the ray and then goes straight. So the third ray is done differently if you're inside the focus. So then it's the 3 slightly less easy rays. How do you measure S prime if the image isn't a real object, just an image? How do you measure S prime if the image is... so you have the lens here and you get a screen and you say, hey, I can see the image on the screen. And then you measure it. In a homework problem, it just says, where's the image? And you just tell us. But in the lab, you will actually... The real images, you put them on a screen, you can see them. So that's how you'll measure it. Okay, so now we're going to use this equation, and we're going to get the same answer we got in all the other cases. That's the exciting thing we're going to do. Okay, here we go. All right. Let's start with very far away, which I think I erased. Now let's see if we can mathematically reconstruct very far away. Okay, object far away. Okay, so let's think about it. We can pretend this one's far away. What would we set F to? I'm sorry. What would we set S to be really far away? You'd want to make it many multiples of F. And what it means to be far away is far relative to the focal length. Okay, so if I'm like here, like 10 Fs away. Okay, so let's give it 10 Fs. Okay, so let's let S equal 10F. Okay, so just usually you'll be plugging in numbers in a problem. Here I'm just going to let F be like a variable. I'm just going to say we have a constant F. Let's do everything in terms of F. So since these are pretty simple algebra, I think you'll be okay with that. Okay, so I'm saying let S equal 10F. That means far away. 10 times relative to F, because that's what really matters. Okay, so now we just plug it in. 1 over S, 1 over 10F. That's 1 over S plus 1 over S prime. That's what we're trying to figure out. Where's the image? Right, equals 1 over F. All right, so this is far. This is where is the image. And then that's F. So you say, okay, well, I'm going to bring this over here, and I need a common denominator, so I'm going to write 1 over S prime equals 10 over 10F. Right, I multiply that by 10 over 10. And bring this over, minus 1 over 10F. Ah, now they both have 10F in the bottom. 10 minus 1 is what? 9. 9 over 10F. Very good. All right, so what is, what did I do? Yeah, so what is S prime? S prime, the image distance is 1.11 F. All right? It's 10/9 of F, which is 1.1111111111. So that would say that when it's far away, the image would show up just past F, which is what we found. Right? When we had this really far away, the image was like right there. So if you make it really far away, just past F, exactly matches the drawing there. And now what about the magnification? Minus S prime over S. Okay, S prime was 10/9 F. right? So we did to get S prime, I had to flip that over, right? 10F over 9. So that's 10F over 9, and it's negative, right? And then over S, what is S? S is 10F. Okay, so the magnification is negative 1/9. The 10Fs cancel, it's 1/9, and there's a negative. So what is that telling you? It's small, okay? So if you're far away, you're going to get an image that is basically right close to here, right close to the focal point, and it's little, like that, which is kind of what we drew. I mean, when I drew it, I didn't really do it at 10F, right? I mean, I don't have a big enough board, and I would need like a ruler. But I drew it at maybe 2 or 3F, and you saw that it was inverted and down here somewhere, if you have that drawing still. You can also see this in the real world. Like if you want to if you have a lens and you want to know what its focal length is, you go find some really high lights, which we have here. We have really high lights here. And you get right under the really high light, and then you hold this here, and you look at an image of the light right on the board, right there. So it's making a sharp image of the light. And it's smaller, it's inverted, you can't tell because it's round, right? But if you measure this, that's basically F, right? The focal length of that thing is like a foot, because there's about 1 foot here. It's slightly past F. F is really like maybe there, but you can see that. So here, put that on yourself. Just look at that. And then, hold it. Here, take it. There you go. And see how heavy it is. Look at what I have to carry around. Look at the sympathy. Where's the sympathy? Oh, my God. Okay. This is all about me feeling better about myself, right? Isn't that why we're here? All these questions. Okay. Oh, sorry. Here they are. Let's get some more questions here. Okay. Yeah. Sorry. How do you measure S prime if the image... Okay. Here we go. Yeah. So how do you measure S prime if the image isn't a real object, just an image? Oh, yeah. We talked about that. That's you. You'll put it on a screen. What does the negative sign of the magnification equation mean? It means the image will be inverted. Right? So the fact that we got negative 1/9 here, negative, is why, you notice every one we did, the images kept ending up upside down. So the negative means it's inverted. That's why that negative is almost always there. Right? Would an m greater than 1 mean it got larger? Yes. Why is magnification negative value? Yeah, because it's inverted. Fundamentally, why? Just trace the rays and convince yourself. That's just what's going to happen because of Snell's law. Okay, so let's see. What did we do? We did object really far away, right? We can do a few more. It's very exciting. Oh, dear. Let's see how fast we can go and do a few more. Just to prove to you that it works. That's what we're trying to do here. Okay, have some confidence in this equation. Let's do object at 2F. That was the one where it looked like, which I also erased, it looked like it made like the same size, but just inverted and also at 2F. Okay? Object at 2F means that S equals 2F. So here we go. 1 over 2F plus 1 over S prime that we're looking for, the image position, equals 1 over F. Well, common denominator, 1 over S prime equals 2 over 2F. Right, I'm just multiplying it by 2 over 2. Multiplying it by 1. Minus 1 over 2F. What is 2 over 2F minus 1 over 2F? 1 over 2F. Right, so what is S prime? 2F. Cool. Right? If you put the object at 2F, here it is, I drew it here. If you put the object at 2F, the image ends up at 2F. Right? What's the magnification? Magnification equals minus S over S prime, S prime over S, sorry. And, well, here they're both 2F, right? This is 2F and that's 2F, so it's minus 1. Right, so that's what's special about having the object at 2F, is that it makes an exact size replica of itself, but just inverted, and the same distance from the lens. Right? Let's do another one. What about the object just outside of F? Here we go. Then we would say S, let's do 11/10 F, right? What would S be 11/10 F? Oh, I erased another one. I erased all of them. Oh, well. Yeah, so that would be the case where we had it like right here. And what happened? It made a really big one, really far away, didn't it? Let's see if that happens. 1 over 11 tenths f plus 1 over s prime equals 1 over f. Right? So, I mean, we could move fractions around now, or we could move fractions around later. Yeah, so basically I would make it easier. I'd put this 10 up at the top and put the 11 there, right? 11 tenths in the denominator means 10 over 11f. And then that's why you would make this 11 over 11f. And then when you bring it around, you'll get 1 over s prime equals 11 over 11f minus 10 over 11f, which is 1 over 11f, right? And you'd get that s prime is 11f. The image shows up at 11 times the focal length. Wow. Right? So if you put the object here, the image is going to show up way over here. Because remember when I drew the rays, I had to do a really long time for them to come back together. I don't have enough boards to keep all this up, I guess. And then you'd say, what's the magnification? Minus the image distance, 11f. Right? Over the object distance, 11 tenths f. And what is that? Minus f's cancel, 11's cancel. It's 1 over 10, 10. Magnification is negative 10. Okay. So I couldn't really draw that case because it's too big. Okay. But that was the case where if you look back at your notes, you had it right here, and it was way out here really big. The math agrees. The math is never wrong. Okay, let's look at one more. What if we put the object at f? Oh my God. Object at f. That would be s equals f. 1 over s is 1 over f, plus 1 over s prime equals 1 over f. 1 over s prime equals 0. S prime equals infinity. So the image would show up at infinity. Right? That's what we drew. Remember the two parallel rays? Just parallel forever. Number 1 and number 2 were parallel right over there. And we said it must be at infinity. What's the magnification? Negative infinity over f, which is equal to negative infinity. Oh yeah, but s is f. Yeah, let me put an s there. And that s is f. So s prime, s infinity, yeah. So the point is it doesn't make an image, right? It makes a giant image at infinity, but you can never get to infinity, so you're never going to get there. Don't even try. Just give up now, okay? What if... Okay, so here's the exciting... is it the finale? Yes, it's the finale, so let's go real slow. This is the cliffhanger. Cliffhanger. Let's put the object inside f. No, s is 3/4 f. Right? We drew it and it was just crazy. Rays were diverging, worlds were colliding. So here we go. 1 over s, 1 over 3/4 f, plus 1 over wherever the image is, equals 1 over f. Right? Okay. So I would probably mathematically do this by putting this 4 here and putting that 3. That was on purpose, by the way. That was my teenager mathematically. Then I'd call this 3 over 3f. Like that, right? Then when I bring it over, it's going to be 1 over s prime equals 3 over 3f minus 4 over 3f. Yeah, which is minus 1 over 3f. Sorry, mental lapse for a minute. So what do you get when you need to solve for the image position of that? It's minus 3f. What? That's weird. But what is the magnification? Because that's minus, then it's minus 3f over 3/4 f, positive. And now those two minuses are going to cancel out, and we're going to get like 4. No, 3. No, is it 4? No, it's 4. My notes say 3. We got a positive number. So two weird things happened when we put the object inside the focus. One weird thing is we got a negative position, and the other thing is for the first time we got a positive magnification. Bum, bum, bum. Come back Thursday. You probably know what's happening. Things just got weird, you know. You could watch online to get a virtual explanation. Thank you.